Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you take a state-of-the-art supercomputer today and you feed it the mathematical equations for two black holes colliding, it will take weeks of just nonstop processor melting grinding to give you the answer.
Yeah, and that's if the simulation doesn't crash halfway through, which, it often used to.
Right. I mean, we are talking about tracking the absolute most extreme violence in the cosmos. It's a collision so powerful that it physically bends the geometry of reality itself.
Which is incredibly hard to calculate. The numbers get unimaginably huge.
Exactly.
Yeah.
But there's this team of physicists have recently published some research suggesting that you might be able to get the exact same answer using basically the mathematics that explains why your morning coffee gets cold.
It is. It's one of the most counterintuitive proposals in modern astrophysics right now.
It really is. And if you follow astrophysics at all, you know about this enduring frustration, right? With the two great paradigms of physics. You've got quantum mechanics and thermodynamics on one side, and then general relativity on the other.
And they notoriously refuse to speak the same language. It's like they're operating in two completely different universes.
Right. So what we're looking at today is a tangible mathematical bridge between them. We are talking about how the ultimate agents of cosmic chaos are, well, secretly governed by the mundane physics of your kitchen.
Yeah, the historical divide you just mentioned, that's really the core of the whole problem. General relativity, Einstein's masterpiece, it's the ultimate theory of the macroscopic.
The big stuff. Planets, galaxies, gravity.
Exactly. And it is entirely deterministic. So if you know the precise state of space-time right now, Einstein's equations should, theoretically at least, tell you exactly what space-time will do a second from now.
A causes B every single time.
Right. But thermodynamics, on the other hand, is a statistical science. It does not care about the deterministic path of individual atoms. It relies entirely on probability and macro averages.
Like, you don't track every single water molecule in a boiling pot. You just measure the overall temperature.
Precisely. So to suggest that you can bypass the deterministic tracking of a black hole merger and instead treat the collision like, say, a mixing of two hot gases, that is a radical departure from how we've calculated these events for decades.
It's nuts. But before we get into how a black hole could possibly behave like a mixing gas, I think we really have to establish what exactly is happening during one of these mergers. Like, let's look at the actual physical crash.
Good idea. Visualizing it is key.
So we've got two black holes locked in this decaying orbit. And because of the sheer mass involved, they're dragging space-time along with them. They're spiraling inward, approaching, a significant fraction of the speed of light, and they eventually touch.
And that exact moment of contact is where the physics gets incredibly hostile. You have to remember that a black hole, it's not a solid object.
Right. There's no surface.
No surface you can knock on. The black hole is just a region of space where gravity is so intense that the escape velocity exceeds the speed of light. The boundary of that region is the event horizon.
So it's just pure math,
Yes,
essentially. A mathematical line in the sand.
Exactly. When two black holes merge, you are watching two purely mathematical boundaries in space-time colliding and reshaping each other. The event horizons deform, they reach out toward each other, and they snap together into a single, highly distorted, sort of peanut-shaped horizon.
I've always loved that visual. A giant cosmic peanut. And the energy released when that snapping happens is staggering. I mean, a typical merger can release more energy in a fraction of a second than all the stars in the observable universe combined.
It's an output of power that literally outshines everything else in the universe put together.
But here's the mechanism I really want to understand. If there's no actual physical matter colliding, like there's no rock, no gas, just event horizons, what exactly is carrying that energy away?
That's the wild part. The energy is carried away by the very fabric of reality itself. When those horizons merge, the surrounding space-time is subjected to catastrophic stress.
It's getting stretched and pulled?
Right. And general relativity dictates that accelerating masses produce gravitational waves. So just as an accelerating electrical charge produces electromagnetic waves, accelerating masses produce ripples in gravity.
So in the final moments of that spiral, and especially during the actual merger, the black holes are just churning space-time into waves.
Yes. They are converting a massive portion of their combined mass directly into the energy of these gravitational waves. Space-time itself is stretching and squeezing, undulating outward at the speed of light.
Wow. Okay, I want to use an analogy here to help visualize this. If space-time is a trampoline, this collision isn't just dropping a bowling ball on it. It's like two bowling balls smashing into dust, sending these massive ripples across the entire surface of the trampoline.
That's a great way to put it. The trampoline mat itself is what's carrying the energy away.
Okay, so we have this wildly asymmetric, wobbling, freshly merged black hole. It's highly unstable. And physicist Monica Rincon-Ramirez describes this exact phase with some really striking imagery. She points out that immediately post-merger, the remnant black hole is ringing like a struck bell.
Yes, the ring down phase.
Right. It vibrates and it radiates away excess energy through those gravitational waves until it finally settles into a calm, stable state. But wait, a bell rings because the metal physically vibrates and displaces air molecules. A black hole is, as we said, empty space, banded by a horizon. What is physically quivering if there is no matter there?
That is the perfect question to expose just how weird general relativity is.
Oh, wait.
When we say it rings, we're talking about a phenomenon called quasi-normal modes.
Quasi-normal modes, okay.
Yeah. Think of space-time as a highly taut elastic medium like your trampoline mat. The event horizon is perturbed, meaning its geometry is highly irregular, like that peanut ship we mentioned.
Right, it's all lopsided.
Exactly. And because a black hole naturally wants to be perfectly smooth and spherical, or at least oblate, if it's spinning, the natural laws of gravity force that irregularity to smooth out. The ringing is the actual metric of space-time oscillating.
So the horizon is violently shifting from elongated to compressed over and over.
Yes, shedding the energy of those deformations as gravitational waves. It's shedding its asymmetries. And as it sheds them, the amplitude of those oscillations decays exponentially. That decay, that fading out, is the ringing stopping.
Okay, so the ringing is literally the new black hole ironing out its own wrinkles by throwing gravitational energy out into the universe.
Ironing out its wrinkles is a brilliant way to describe it.
And when that ringing stops, when the wrinkles are all ironed out, we are left with the final remnant. But what fascinates me here is the sheer simplicity of that final state. Based on the no-hair theorem in astrophysics, once a black hole settles down, all of the chaotic history of the collision is just wiped out, right?
Completely erased.
The final object is defined by only two properties, mass and spin.
Well, technically the no-hair theorem allows for three properties. It's mass, spin, and electric charge.
Oh, right, charge.
But, in a realistic astrophysical setting, black holes have negligible charge because they would just quickly attract opposite charges from the surrounding plasma and neutralize themselves anyway.
So practically speaking, it's just two.
For all practical purposes, yes, you are entirely correct. We only care about two parameters: mass, which tells us the size of the event horizon, and spin or angular momentum, which tells us how fast the black hole is rotating.
So all the intricate details, the varying masses of the original black holes, the specific angles they collided at, the complex geometry of the merger, all of that is just gone.
All of that information is swallowed by the horizon or radiated away into the universe.
Mass and spin, that is it. But if the final state is just two simple numbers, why on earth do we need supercomputers running for weeks to find them? I mean, if I smash a 2-kilogram ball of clay into a 3-kilogram ball of clay, I don't need a supercomputer to tell me I have a 5-kilogram ball of clay.
Because black holes do not obey simple Newtonian arithmetic. When you smash those two balls of clay together, they aren't radiating, 10% of their mass away into the geometry of empty space.
Fair point. The energy loss is massive.
Right. The problem lies in the equations we have to use to calculate that loss. Einstein's field equations of general relativity are a set of 10 highly complex, coupled, nonlinear, partial differential equations. The key word there being nonlinear.
Let's drill into that nonlinearity because that seems to be the fundamental bottleneck here for the computers.
Yeah.
When we say an equation is nonlinear in physics, we usually mean the variables feed back into themselves, right?
Precisely. In general relativity, mass and energy tell space-time how to curve. But that curvature dictates how mass and energy move.
A chicken and egg situation.
Exactly. And because gravitational waves carry energy, the waves themselves exert gravity. So you have a situation where the changing shape of space generates energy, which changes the shape of space, which generates more energy. It is just a catastrophic feedback loop.
Wow, so how do you even calculate that?
To solve this mathematically, physicists use something called numerical relativity. They break space-time down into a massive three-dimensional grid. stepping forward in time in tiny, tiny increments. At every single intersection on that grid, for every fraction of a microsecond, the supercomputer has to recalculate the entire 10-component metric tensor.
That sounds incredibly taxing. And if the grid isn't precise enough, the math literally blows up, doesn't it?
Oh, yeah.
I know that for decades, physicists couldn't even get the simulations to run past the first few milliseconds of a merger.
Oh, it was a nightmare for theoretical physicists. The coordinate systems would just fail, the values would shoot up to infinity, and the computer would crash.
Right, because it just couldn't handle the infinite feedback loop. It wasn't until 2005, I think, that Franz Pretorius finally figured out a mathematical trick to keep the simulation stable through the actual merger. So we're talking about an incredibly brutal, computationally exhausting method.
It is a tour de force of human computation. You are tracking the microscopic evolution of space-time geometry through sheer brute force determinism. You're mapping every single ripple, every distortion to see exactly how much mass and spin is radiated away, just so you can subtract that from the initial total to find out what is left over.
Which brings us to the alternate route, the shortcut that honestly feels like a cheat code.
It really does.
The researchers at Penn State, including B.S. Sathipakash, Nathan K. Johnson McDaniel, and their colleagues, are proposing that we don't need to track the deterministic geometry of spacetime step by step. They argue we can bypass numerical relativity entirely by using thermodynamics.
Which is a huge leap.
Right. But to make that leap, we have to look at why black holes and thermodynamics are even allowed in the same room together in the first place. Because for a really long time, they absolutely were not.
Historically, black holes were considered thermodynamic dead ends. I mean, the classical laws of general relativity state that nothing can escape an event horizon.
Not even light.
Right. And if nothing can escape, a black hole cannot emit heat. If an object cannot emit heat, its temperature must be absolute zero.
Okay, that makes sense under classical rules.
But here's the catch. In classical thermodynamics, if you drop a hot cup of coffee, which has a lot of entropy, a lot of disordered microscopic states into a black hole, that entropy vanishes from the observable universe.
Oh, I see. And that violates the second law of thermodynamics.
Exactly. The second law states that the total entropy of the universe must always increase.
Right, because if you could just throw your entropy into a black hole and completely erase it, you're decreasing the entropy of the universe. You are cheating the most fundamental law of nature. And that paradox, that's what led Jacob Bekenstein and Stephen Hawking to completely rewrite astrophysics in the 1970s, isn't it?
It is. Bekenstein was the first to propose the heresy, really. He suggested that black holes must have entropy and that the entropy must be proportional to the surface area of the event horizon, not its volume.
Not the volume, but the surface area.
Yes. So when you throw the coffee cup in, the black hole gains mass, its event horizon physically grows, its area increases, and therefore its entropy increases, satisfying the second law.
Boom, paradox solved. But Hawking initially hated that idea, didn't he? Because if a black hole has entropy, it must have a temperature, and if it has a temperature, it must radiate heat. But we just established nothing can escape a black hole. So Hawking actually set out to mathematically prove Bekenstein wrong.
He did. Hawking applied quantum field theory to the curved spacetime near the event horizon, fully intending to disprove Bekenstein's theory. But instead, he proved him right.
Which is hilarious and brilliant.
It's now considered one of the greatest theoretical discoveries of the 20th century. Hawking discovered that black holes are not completely black. They glow.
Let's break down the mechanics of that glow, because it is crucial for understanding how the Penn State team applies thermodynamics to a merger. The glow is Hawking radiation. But how does empty space near a horizon suddenly radiate particles?
We have to look at the vacuum of space through the lens of quantum mechanics. In quantum field theory, a vacuum is not truly empty. It is this boiling sea of quantum fluctuations.
Just a chaotic mess of energy.
Exactly. Pairs of virtual particles, a particle and its antiparticle, are constantly popping into existence, borrowing energy from the universe, and then instantly annihilating each other to pay the energy back. This happens everywhere, all the time. In your living room, in deep space, everywhere.
But when this happens exactly on the razor's edge of an event horizon, the script changes.
Dramatically. If a pair of virtual particles pops into existence right on that boundary, the intense gravitational gradient can pull them apart before they even have a chance to annihilate.
Wow, so the gravity is stronger than their attraction to each other.
Yes. One particle falls past the horizon into the black hole. The other particle, just outside the horizon, is violently propelled out into the universe. So to an outside observer, it looks exactly as if the black hole just emitted a particle. It radiated heat.
I've always struggled with the mass accounting here, though. If the black hole absorbs one particle and shoots out the other, shouldn't its mass increase, or at least just stay the same? Why does Hawking radiation cause the black hole to slowly evaporate over time?
It comes down to energy conservation. The virtual particle pair was created by borrowing energy from the vacuum. When they are separated, the particle that escapes becomes a real particle with positive energy.
Okay, so the universe gains a positive particle.
Right. So for the universe's energy ledger to balance, the particle that fell into the black hole must have negative energy relative to the outside universe. When the black hole absorbs that negative energy, its total mass decreases.
That is such a brilliant mechanism. The universe balances its checkbook, and the black hole shrinks. And by proving that black holes have a temperature and slowly evaporate, Hawking fundamentally linked gravity and thermodynamics. He finalized the Bekenstein-Hawking formula, which mathematically defines the entropy of a black hole.
And that formula is breathtaking. It incorporates the fundamental constants from almost every major branch of physics.
It's like the ultimate crossover event.
It really is. It includes Newton's constant for gravity, the speed of light for relativity, Planck's constant for quantum mechanics, and Boltzmann's constant for thermodynamics. It perfectly weaves them all together to state that the entropy of a black hole is exactly a quarter of the area of its event horizon.
But here is the massive problem that the Penn State researchers had to confront. Hawking's math, as beautiful as it is, was formulated for static, stationary black holes. A black hole just sitting out there in the void, slowly glowing. It was not designed for the apocalyptic chaos of two black holes colliding at half the speed of light.
Not at all.
Taking the thermodynamics of a quiet black hole and trying to apply it to a violent merger, it seems like trying to use a thermometer to measure a bomb going off.
That's a very accurate comparison. It is a massive leap. The Penn State team, led by researchers like Sathi Prakash and Vaishak Prasad, they had to prove that thermodynamic rules don't just apply to quiet black holes, but to dynamic, rapidly evolving spacetimes.
Spacetimes that are literally ripping themselves apart.
Exactly. They hypothesized that even in the midst of a violent merger, the underlying principles of thermodynamics are still driving the bus. Specifically, they proposed the maximum entropy conjecture for black hole mergers.
Okay, we need to completely define what entropy means in the context of a black hole here, because the standard analogy everyone learns in high school physics is the messy room, right?
Yeah.
A tidy room has low entropy, a messy room has high entropy, just because there are more ways for things to be messy than tidy.
The classic example.
But a black hole isn't a room full of socks and books, it's empty space.
How do you measure the messiness of a completely featureless void?
Well, the messy room analogy is helpful for basic intuition, but to really understand this research, we have to look at entropy in terms of statistical mechanics. Entropy is not just messiness. It is a precise measure of microstates mapping to a macrostate.
Microstates and macrostates. Break that down for me. Think of a digital photograph on your computer screen. The image you see, let's say it's a picture of an apple that is the macrostate. The specific arrangement of millions of individual red, green, and blue pixels that make up that image, those are the microstates.
Okay, so if I change the color of one single pixel hidden in the shadow of the apple, the image still looks exactly like an apple to me. It's a different microstate, but the exact same macrostate.
Exactly. Now, apply that to a gas in a balloon. The overall temperature, pressure, and volume of the gas, those make up the macrostate. The precise position and velocity of every single microscopic gas molecule bouncing around inside the balloon are the microstates.
There's a near infinite number of those.
Right. There are billions of different ways those molecules could be bouncing around that would all result in the exact same temperature and pressure. Therefore, the gas has high entropy. Many, many microstates correspond to its single macrostate.
So how does this map onto a black hole? Because the no-hair theorem says the macrostate of a black hole is completely defined by just mass and spin. But what are the hidden pixels? What are the microstates of a black hole?
That is one of the deepest mysteries in theoretical physics right now. It's heavily researched in string theory and loop quantum gravity. We don't have a fully verified quantum theory of gravity yet, so we don't know exactly what the microscopic building blocks of a black hole actually are.
So we're flying blind on the micro level.
We are. But the Bekenstein-Hawking entropy formula guarantees that they exist. Even if we can't see the individual pixels of the black hole, we know they are there, and we know exactly how many there are based purely on the surface area of the event horizon.
Wow. And this allows the Penn State researchers to treat the black holes exactly like interacting gases. Physicist Eugenio Bianchi brought up this specific gas analogy. He said, if you take a box of hot oxygen and a box of cold nitrogen and you open a valve between them, the gases mix. To figure out the final temperature and pressure of the mixed gas, you don't need a supercomputer tracking the deterministic collision path of every single oxygen and nitrogen molecule. That would be impossible. You would just use the laws of thermodynamics. Nature will automatically drive the system toward the state that has the highest possible number of microstates. Nature maximizes the entropy.
Yes, and nature doesn't maximize entropy out of some cosmic desire for chaos. It happens purely through probability. If a mixed gas has 1 trillion times more microstates than a separated gas, the system is going to statistically settle into the mixed state.
Because it's just overwhelmingly more likely.
Right. So the researchers asked, if nature always drifts toward the highest entropy state simply because it is the most statistically probable, do black hole mergers do the exact same thing?
And their conjecture says yes. They propose that when these two gravitational titans collide, the final remnant black hole isn't determined by the microscopic, step-by-step unspooling of space-time geometry, like the supercomputers calculate. The final mass and spin of the remnant is simply whatever mass and spin yields the absolute highest possible entropy, taking into account the energy that was lost.
The energy loss is the critical variable here. When the gases mix in a closed box, energy is perfectly conserved within the box. But a black hole merger is not a closed box. As we discussed earlier, a massive amount of energy and angular momentum is blasted out into the universe as gravitational waves during the inspiral and the quasi-normal ringing.
Let's talk about the angular momentum loss, because it is fascinating how a gravitational wave can carry away spin. Like, I can visualize a wave carrying away raw energy like a ripple carrying away the impact energy of a stone dropped in a pond. But how does a ripple in space-time carry away the rotational momentum of the black holes?
It takes a little visualization. Think about the geometry of the waves themselves. Because the black holes are orbiting each other, the gravitational waves they emit are not perfectly symmetrical expanding spheres.
They're not just expanding out like a balloon.
No, they are emitted in a spiral pattern, heavily influenced by the orbital mechanics of the binary system. As these ripples propagate outward, they physically twist the space-time they pass through.
Oh, wow. They twist space itself.
Yes. That twisting motion requires angular momentum. By twisting the surrounding universe, the waves are literally sapping rotational energy from the merging black holes and carrying it away into the void.
So the Penn State team has to account for all of this. They know the starting mass and spin of the two original black holes. They know they have to subtract the mass and spin that is carried away by the gravitational waves. And to find the final state, they need to find the configuration that maximizes entropy under those specific conditions. How did they actually execute this test? How do you map this mathematically?
They constructed a methodology based on hypothetical states. Because, they couldn't just assume their thermodynamic theory was correct from the jump. They needed to compare it against the deterministic results generated by those massive numerical relativity supercomputers.
A gold standard.
Right. So they took the initial parameters of a known simulated merger. Then they mathematically generated a sequence of hypothetical remnant black holes.
What do you mean by a sequence of hypothetical remnants?
Imagine a graph. The researchers know a certain amount of energy and angular momentum is going to be radiated away. So they created a mathematical spectrum of possible final black holes, each with slightly different combinations of final mass and final spin that still obey the basic laws of conservation.
Like a lineup of possible suspects.
Exactly. And for every single one of those hypothetical black holes on the spectrum, they calculated its thermodynamic entropy using the Wittgenstein-Hawking formula.
So they're essentially looking for the peak of a curve. They map out the entropy for all the possible final states, looking for the specific mass and spin combination that represents the absolute highest entropy, the ultimate thermodynamic sweet spot for that specific collision.
Precisely. They charted the entropy evolution, accounting for the fluxes of energy and angular momentum being radiated to infinity by the gravitational waves. They watched the curve rise as the system evolved, looking for the apex, the maximum entropy state.
And the results they found are the core of this entire revelation. When they found that peak, the hypothetical black hole with the highest possible entropy, they compared its mass and spin to the mass and spin calculated by the grueling, weeks-long supercomputer simulation.
Yeah.
And the values matched. The entropy curve peaked at virtually the exact same mass and angular momentum predicted by numerical relativity.
The agreement was absolutely staggering. To bypass the microscopic geometric tracking entirely, to rely purely on the statistical laws of thermodynamics, and to land on the same target, it is a profound validation of the conjecture.
I have to challenge this here, because the literature notes that the values matched, but they matched within a margin of error of a few percent. You're saying they got within a few percent. But in astrophysics, a few percent can be a massive discrepancy. I mean, a few percent error in an orbital calculation can mean a satellite misses Mars entirely and shoots off into deep space.
That's very true.
So why should we accept a few percent margin of error as a stunning victory here, when numerical relativity gives us a much more precise number?
That is a highly valid critique, and it is one the physics community wrestles with. The thermodynamic calculation is not currently a replacement for numerical relativity when we need absolute pinpoint precision for observational templates.
Like for LIGO.
Right, like when the LIGO observatories are trying to match a specific gravitational wave signal to a real-world source. But you have to separate the practical utility from the theoretical revelation. The few percent discrepancy likely arises from the approximations required to model the radiation fluxes.
The exhaust, basically.
Yes, the exact amount of energy and spin carried away by the waves during the most chaotic fractions of a millisecond. We don't have perfect analytical models for that split second of peak chaos.
So the error isn't in the thermodynamic principle itself. The error is in how accurately we are measuring the exhaust of the collision.
Exactly. The fact that the maximum entropy principle gets us within a few percent of the deterministic calculation is not a failure of precision. It is proof of a fundamental underlying mechanism. It proves that the universe is actually obeying these statistical laws, even in the most extreme gravitational environments.
I want to try an analogy here to see if I'm fully grasping the magnitude of this. Let's say I want to figure out the exact shape and layout of a shattered glass vase after dropping it off a building. The numerical relativity approach is like tracking the exact aerodynamic trajectory, mass, and velocity of every single shard of glass as it falls, computing how they deflect off each other in midair, and plotting exactly where they land on the pavement.
Which is impossibly complex. A perfect description of the deterministic approach.
Right. But the thermodynamic approach they just tested is like ignoring the shards completely. Instead, you just measure the total kinetic energy of the vase before it dropped, measure the total heat generated when it hit the ground, and use statistical probability to deduce that the shards must have arranged themselves in the specific pattern that maximizes the entropy of the impact. And you get almost the exact same layout.
That analogy captures the essence of the breakthrough beautifully. You are swapping a microscopic geometric tracking problem for a macroscopic thermodynamic state problem. By verifying that the final black hole remnant corresponds to the state of maximum entropy, the researchers have essentially proven that the violent dynamics of spacetime geometry are fundamentally constrained by the same statistical laws that govern heat and gases.
This circles back to the concept of cosmic amnesia, or what the void remembers. When those two black holes merge, the resulting remnant forgets the intricate geometry of the collision entirely. It doesn't retain any memory of the specific paths the event horizons took as they twisted together.
It just lets it all go.
The universe essentially says, that was too chaotic to keep track of. Let's just default to the most statistically probable state. The black hole sheds all that complex geometric information through the ringing of gravitational waves, driving itself toward maximum entropy until only mass and spin remain.
Which forces physicists to grapple with a monumental question. B.S. Satyaprakash, one of the leading researchers on this project, highlighted that this intersection goes far beyond our established models. We have always treated thermodynamics as a consequence of particles moving around in spacetime. But if spacetime itself, in the form of a purely geometric black hole, obeys thermodynamics, it suggests something deeper.
It suggests that the fabric of reality isn't just the stage where physics happens. The fabric itself is governed by statistical mechanics.
Could entropy maximization be the fundamental organizing principle of the universe? It is a question that flips our understanding of gravity on its head. There is a growing movement in theoretical physics right now, pioneered by people like Eric Verlin, suggesting that gravity might not be a fundamental force at all.
Wait, not a fundamental force?
No. Instead, gravity might be an emergent phenomenon, a byproduct of the universe constantly trying to maximize its entropy. This research from Penn State provides incredibly compelling mathematical evidence that such a connection exists at the most extreme scales.
That is a staggering paradigm shift. If you are a physicist who has spent your entire career looking at general relativity as the absolute bedrock of gravitational physics, seeing evidence that relativity might just be a macroscopic side effect of thermodynamics. That must be both terrifying and exhilarating.
It's the kind of discovery that paves the way toward a unified theory of quantum gravity. By showing that the deterministic equations of Einstein and the statistical equations of Boltzmann arrive at the exact same destination, we are slowly peeling back the layers of the illusion. The universe doesn't have a separate rulebook for black holes and a separate rulebook for hot gases. There is one underlying architecture.
This completely reframes how we look at the cosmos. We started this discussion visualizing the most violent, unimaginable event in nature. Two massive singularities ripping through the fabric of space, unleashing more energy than the rest of the visible universe combined. It is so easy to look at an event like that and think it belongs to a realm of physics completely alien to human experience, a realm of hyper-complex tensor calculus and abstract geometry.
But the reality uncovered by this research is far more elegant.
Elegant and almost poetic. The forces that dictate the violent birth of a new black hole are the exact same forces that dictate why a drop of ink disperses in a glass of water. It is all driven by nature's inescapable march toward maximum entropy. If the most extreme light-crushing objects in the cosmos are ultimately bowing to the exact same statistical laws that dictate the everyday thermodynamics of our lives, the universe is far more unified and far more deeply interconnected than we ever dared to imagine. It proves that whether you are looking at a messy room, a cooling cup of coffee, or the collision of gravitational titans, you're watching the exact same invisible hand at work.
It is a remarkable testament to the universality of physical laws.
It truly is. It's a reminder that the deepest mysteries of the universe might not be solved by building bigger supercomputers, but by recognizing the patterns that have been sitting in front of us the entire time. Thank you for joining us on this journey today. Keep questioning the universe around you and never stop looking for the hidden rules that bind it all together.